atomic structure is governed by 4 quantum numbers. Actually, it's governed by something a little more than that, but the major things about atomic structure, at least the things we get in an introduction, are governed by the 4 quantum numbers. One quantum number is the orbital quantum number, the n that we had, the n that comes from the quantization of angular momentum. Okay, so we have the orbital number 1, 2, 3, 4, 5, 6, 7, so forth. We have an angular momentum quantum number. There are rules for these quantum numbers. The angular momentum quantum number has to be 0, 1, 2, 3, 4. It can't be negative. And it can't be as big as the orbital quantum number. So, for example, in an n equals 1 orbit, the angular momentum has to be 0. It can't be negative, and it can't be as big as the orbital quantum number. And it has to be a whole number, an integer. Okay, for n equals 2, we could have angular momentum L equals 0 or L equals 1. Now, both of these are non-negative and less than 2. And for n equals 3, we could have 0, 1, or 2. We have a magnetic quantum number that affects the alignment of the magnetic field of the atom with an external magnetic field. It tells us how strongly we're going to tend to line up with an external magnetic field. And the magnetic quantum number can be positive or negative, and its magnitude can be as big as but not bigger than that of the angular momentum quantum number. So, for example, if the angular momentum quantum number is 0, the magnetic quantum number has to be 0. It can't be bigger in magnitude than the angular momentum number L. So ML would be 0 when L is 0. However, if L is 1, then ML could be negative 1, 0, or 1. It can be positive or negative, and it can be as big as but not bigger than L. So ML would be negative 1, 0, or 1. If L is 2, then ML could be negative 2, negative 1, 0, 1, or 2. And then we have a spin number that tells us how the electron is going to line up with an external magnetic field, either a positive or negative 1/2. Now, to get to atomic structure, we see that if the orbital is the n equals 1, the angular momentum has to be 0, the magnetic number is 0. There's only one choice for these 3 quantum numbers, and there's just 2 choices for the spin. So there are only 2 possible combinations, 1, 0, 0 plus 1/2, 1, 0, 0, negative 1/2, for the quantum numbers of an n equals 1 electron. This is important because there's this exclusion principle, the Pauli exclusion principle, which tells us that we can't have 2 electrons in the same atom that have identical quantum numbers. So there has to be a difference somewhere in the quantum numbers in order to have more than 1 electron. Well, we see that there are only 2 different sets of quantum numbers for an n equals 1, so there are only 2 possible electrons that can go into an n equals 1 orbital. This means that if we had an atom that had more than 1 electron, we could have at most 2 in that n equals 1 orbital. Now, if we go to the n equals 2 orbital, for L equals 0, we again get ML equals 0, spin plus or minus 1/2. The L equals 0 case is just like it is for n equals 1, and there are 2 possible sets of quantum numbers. N equals 2, L equals 0, ML equals 0, and S equals plus 1/2, and the same things with S equals negative 1/2. So there are 2 possible L equals 0 electrons in the n equals 2 orbital, and that's the 2 that we have here. The same thing is going to be true for the n equals 3. The L equals 0, we're going to have the same 2 combinations of the L, ML, and S quantum numbers in the n equals 3 orbital, and we'll again have 2 possible electrons there. For the L equals 1 orbital, ML is negative 1, 0, or 1, and now we have several possibilities. Okay, we can have n equals 2, L equals 1, ML equals negative 1/2, and S equals 1/2, or the same things with S equals negative 1/2. Similarly, we could have 2 and 1 here, but with 0 and then plus or minus 1/2. That's 2 more possibilities. The 2 here, the 1 here, and the 1 here, and 2 more possibilities for the spin. That's a total of 6 combinations of L equals 1 quantum numbers in the n equals 2 orbit. So in the n equals 2 orbital we have 2 L equals 0 and 6 L equals 1 possible electrons for a total of 8 possible electrons. In a multiple electron atom then we would have in the lowest energy state we would have 2 n equals 1 electrons and 8 n equals 2 electrons. We then go into the n equals 3. And we have the same types of rules. It's just that when L equals 2, which is now possible for n equals 3, we have 5 choices for our ML. And for each of those, we have 2 choices for S. So we have 10 possible n equals 3, L equals 2 electrons, for a total of 18 in the n equals 3 shell.